Okay, good evening, everybody. And welcome to another session of organic chemistry. In today's session, we are going to conclude our discussion on chapter 16, which is concerned with the chemistry of aromatic compounds. But before we do that, a couple of announcements. Just a reminder that the first class exam is scheduled for this coming Thursday, which is February 6th. And also our own work assignment, the end of chapter 16 questions in our assignment is due on Friday. That is February 7th at 11 p.m. Okay, so let us get this session started. I know you guys want to go over the quiz question that you've just taken, right? Okay. Okay, Chad, can you go ahead and read this first? Okay, thank you. Okay, so what we have here, we have this synthetic scheme in which we are converting this molecule here, toluene, to this molecule right here. And according to what the question says, this scheme is flawed. In other words, there is something wrong with this synthetic scheme. So before we actually figure out what the correct scheme should be, let us see what is going to happen here. Let us follow this scheme and see exactly what we are going to get. Okay. So here we're starting with toluene. Okay, what is the first reaction? What kind of reaction is the first one? What is it? Acylation? Okay, Friedel-Crafts acylation. Very good. In other words, we are taking this molecule here, this reagent. It's an acid chloride. In the presence of aluminum chloride as a catalyst. Okay. Okay, what product do you expect us to obtain? Let us label this here. This is carbon 1, carbon 2, carbon 3, carbon 4, 5, and 6. Where do you expect the AC group to go? The para position? Okay. Because okay, because the methyl is an auto para director, exactly. The methyl group, and the same thing with all alkyl groups, are auto para directors. So therefore, we expect to get this. Okay, so the AC group has replaced the hydrogen on carbon number 4. Okay, now the next step. What is the next step? Step number 2. What does that reagent do? Nitration. And what does it do specifically? It will replace the hydrogen on benzene with a nitro group, right? Okay. Okay, so now we have this. Nitric acid in the presence of sulfuric acid, what it does is to give you nitration. In other words, we are going to introduce a nitro group into the benzene ring. And where do you expect it to go? Which of these carbons here? 2, okay. Now, why do you say 2?
Because the CH3CO is meta-directed.
Okay, let us see here. So you say the nitro is going to be here, and now we have this here. You say because this is a meta director. Do you think that is what is going to drive this reaction? That substituent. Of these two here, which will drive the reaction? The methyl, because the methyl is an activator. Okay? So it just so happens that both of them are directing to the same position. The methyl is an autopara director, so it directs to this position here. Also happens that the AC group, this group here, is also directing to the meta, it's a meta director also directing to the same carbon atom. Okay. Now, then what do we have? Now we have step number 3, hydrogen followed by palladium. What does that do? What does it do? To convert the carbonyl that is attached to benzene to a CH2. Okay, unfortunately, it also converts the nitro group to an NH2, to an amino group. So that is the problem with this synthetic scheme. So this is what you are going to get. The nitro becomes an amino group as a result of this reaction with hydrogen and catalyst. And of course, this here now becomes a CH2 group or a methylene group. The carbonyl is now converted to CH2. So that is why they tell you that this process is flawed, because this is the product they want. You follow that? Okay? So if you follow this scheme, this is the product you are going to get, not this here. Okay, now supposing now, let us now give the correct synthetic scheme that will give this. Okay, what do we do? Okay, we start with what do you want to start with? Keep in mind, at this point, you just have to give the correct synthetic scheme. You don't have to follow this. Okay, so what do you want to do? Nitration. Okay, so you want to do nitration. Okay. Why do you want to do nitration first? Okay, nitration, so where do you expect the nitro to go? 2 position, okay. Well, we take that. Okay, then what do you do now? What do you do? Alkylation, Friedel-Crafts. Keep in mind, you cannot do Friedel-Crafts alkylation when you have a very strong electron withdrawing group attached to benzene. So therefore, let us take this out. Okay, so this will not work at this point. Okay? So what do you want to do? Yes. Alkylation first. Okay? But you could do acylation. Even you could actually do alkylation here. Yeah, Friedel-Crafts alkylation, you know, you don't really need to do acylation at this point, right? Make it easy for you. So you could, since we need to introduce the 2 carbon here, so we could simply do a Friedel-Crafts alkylation. Okay, that's chloroethane in the presence of aluminum chloride, and so that gives you this here. right? And then what do? Do your nitration, exactly. So this is actually fairly simple. Hopefully, by going through this here, you get to learn or to recall all of those reagents and what they do. Yes.
I'm saying that there are two alkyl groups on the benzene and non-case.
Yeah, you are going to get a mixture, but at this point, we are assuming that you know how to separate the mixture. Okay. Okay, so we get this. Okay. Now, yes.
Why did you say that you can't do alkylation of the
Okay, Friedel-Crafts alkylation, one of the limitations of Friedel-Crafts alkylation and acylation is that whenever you have very strong electron withdrawing group attached to benzene, it will not go. Because those electron withdrawing group, they're taking electron away from the ring system. So it just will not go. Okay, now suppose, yes, go ahead. Yeah, you could do that. It's just an extra step that you're doing. Okay, in other words, you want to do acylation, then you do hydrogenation to convert back to AT group, okay, and then nitration, right? Yeah, you could do that. Huh? It's just an extra step. You're just giving yourself some more work to do. Yes. Okay, because the alkyl groups are auto para directors. They will always direct to the auto and the para position. But since the para position is already taken up, then naturally they will go to the nitro goes to the auto position of either one of the alkyl groups, either here or here. And that was the question that was asked earlier, and I said you will get a mixture. Okay, now supposing you have this. I don't want to erase that. Supposing I have this here. Okay, well, let me go to a new page. Supposing this is what I want you to make. Okay, from benzene, just a twist on what the last question that you just did. Okay, how will you do that? Yes. Okay, nitration, very good. You want to, you say nitration? Okay, well, let us see. Not that I agree with you, but let us see. Okay, so you have nitrobenzene. Okay. Then now you cannot do acylation anymore, right? Or alkylation. Okay, so we don't want to start with that. Okay, so what do you want to do? The reason I bring this up because it is very important when you are making this decision. The sequence is very important. Okay, so what is the first thing you want to do here? Huh? Okay, you want to do alkylation? Okay. Friedel-Crafts alkylation using methyl chloride? Okay. Why do you want to do that? That is good, by the way. Because it will direct the AC to the para position? Okay. Okay, now we've done that. What is the next step? nitration. Okay, you want to do nitration. Okay. And you want the nitro in the auto position. Now, what is the next step? Hydrogenation. Okay. Oh, okay. Oh, okay. Now I see where you guys are, what you want to do. There is a reagent I've not given you before that I want you to use. And that is this here. I see why you do that. Okay, sorry about that. If you take this ion in the presence of dilute acid, this here will selectively transform. That's why I give you 2 out of 4. Okay, that reagent will selectively transform a nitro group to an Na2. Okay. I see that was why you guys were trying to go around the doing that the reduction. Okay, so we have this. Okay, now what you do that, then what is the next step? See? Okay, you want to go back on your scheme?
Yeah.
That you know better. Now that you know better, right? Okay. Okay. Now you have a new reagent. So let us go back here. So you don't want to do nitration, right? Okay. So what do you want to do now? Acylation. Exactly. Yes. Say that again. Oh, no. Na2 is a very powerful, the activating agent. Really a very powerful activating agent.
So after putting it in a solution, still done acid.
If you do with the nitro.
The way you just did it, it wouldn't work, right?
Okay, but don't forget now, once you do the acylation, okay, you could not do the, once you do nitration, you cannot do the filter cap acylation. Okay?
Right, so the method you did wouldn't work, right?
Which method? The one I want to do now?
When you turn nitration into NH2.
No, it will work. Just the sequence, just a minute. Okay, so now we want to do acylation. Okay, because now we have a methyl group attached to benzene, so you could do filter cap acylation at this point, right?
You wouldn't have been able to do it because they're strong. You would have been able to because it's too strong. I know it wouldn't work, right? No, you would go with a class.
Okay, so we do that, right? Okay, now at this point we want to do nitration. And then that gives us the nitro group in the auto position relative to the methyl group, right? And then at this point, what do we need to do? We now use the reagent I just given you, ion in dilute acid. Okay? And that will specifically transform the nitro group to the amino group. And at this point also, nothing will happen to the carbonyl of the ketone. Yes.
The NH2 group, isn't that, I said, not, it's not an electron,
The Na2 is an autopara director.
yeah, but where, electron withdrawing, it's not an electron.
No, it's electron donating.
Right, so why would it affect the, not add, if you added it first, you had the NH2 on the group.
But it's also autopara director.
Oh,
Okay, because once you have the Na2 in there, it will take over the direction. And then whatever you want to do will go to this carbon here. Okay, you follow that? Okay, Kiara, and that was why that will not work if you did that.
I was kind of saying it wouldn't work. I thought she was trying to say it would work.
Oh, okay, okay. Okay, anyway, so now, so anytime you want to transform a nitro group to an amino group, this is the reagent you need right here. Okay, so let us do the next one. Okay, Victoria. I think we have two Victoria. Victoria Larson, right? Okay. Can you read it for us? Okay, thank you. Okay, so now what we want to do, starting with benzene, and using fiddle-crab alkylation, they wanted to make this compound here. Okay, so how do we do that? Let us start. Keep in mind, at this point, we need to introduce two carbon atoms. We need to form a new carbon-carbon bond to the benzene ring. So what kind of reaction should come to your mind at this point? Fiddle-crab alkylation. Okay, very good. So we do a fiddle-crab alkylation. And that allows us to join two carbon atoms to the benzene. Okay, now what do you do now? What do you do next? Keep in mind we need to form an alcohol. This takes us back to last semester. Bromine, okay. What reagent do you need for that? Is it Br2? Yeah, well, you could use Br2. That's not selective. You want something selective for this here. Because Br2 could also do this, to replace an hydrogen on this here or on this here. Yes. Yeah, MBS, yes. The MBS is specific for replacing an allylic hydrogen with bromine. Very specific. Okay? If you use bromine, bromine could replace any hydrogen that is attached to an sp3 carbon. Bromine and light could do that. In other words, if you did this, okay, you could get this. Granted, you get your product, just so happen you don't have too many carbons here, so that might just be okay. You also get this. Okay, so you could get a mixture. No. Okay, but if you really want to be very specific in terms of what we want to make, replacing one of these benzylic hydrogen with bromine, the best reagent to use is MBS. So I will take MBS and bromosuccinimide in the presence of any peroxide and light. Okay, now what do you do from there? Elimination. Okay, potassium hydroxide. Okay, like I said, this takes us back to last semester. Okay, now this you are going to form an alkene at this point. Okay, and then what do you use to go from here to here? What reagent do you need? Borane, okay. Okay, that's anti-mechanical addition of water. Very good. And then you follow that up with hydrogen peroxide in basic medium. Okay? Very good. Hopefully this is a review to all of you. It is important that you know those reagents. There is no way around it. Okay? Reagents are the ABC of the alphabets of organic chemists. You need to know them. You cannot do anything without knowing your alphabet, right? Okay, the same thing as an organic chemist, you cannot do anything without knowing those reagents and what they do. Okay. Okay, Erin, I got your name right this time. Okay, thank you. So now they want us to start from benzene. And make this molecule here, benzene sulfonic acid. That is benzene sulfonic acid. Then you have 4-chloro and 2-propyl. Okay, so once again we have to design some kind of synthetic strategy to do that. Okay, so how do you do that? Let us start with benzene. Keep in mind at this point you have an ethyl group. Oh, I'm sorry. And I was saying it too, and I was saying it too. Sometimes I am on autopilot. Okay. Okay, so now we have the, let us start with benzene, of course. Okay, let's do a little bit of analysis here. Okay, so you have the propyl group and the chlorine. These are both auto-para directors. So therefore, you know that we have to do something different here because there is no way you are going to be able to make this directly. Okay? Those are auto-para directors. Of course, this is a meta director here. So what synthetic approach are you going to use? What would be the first reaction? Keeping in mind that you need to direct something to meta to this group right here.
Acylation.
Acylation? Okay. You want to do acylation? I think Cinda like acylation.
This is why I cried.
Free to have acylation?
Right.
Let me be consistent here. Let's put it right here. Okay, now after that, what do you do? Now you want to? Chlorination? Okay, very good. So you know the chlorination, chlorine with iron 3 chloride. Once you know those reagents, you find that most of these things are actually very easy to do. Just a little bit of thinking will get you to where you want to go. And then the chlorine comes here. Okay, now what do you do after that?
H2 repeated.
Okay. You want to reduce, right? Hydrogenation. You want to reduce the carbonyl attached to of a ketone attached to benzene to a CH2. Okay, now what? What do you want to do now? Sulfonation, okay. Okay, once again, just knowing the reagents is what is important here with a little bit of critical thinking. Okay, this group will take over the direction, and it is an auto para director, so to place this right here. Okay? Very good. So let's do the last one here.
Wait.
Oh.
Will it matter if you did the sulfonation before the H248?
No, at this point, let us see here. No, it doesn't really matter at this point. Okay? Okay, Olulade, could you read this for us? Okay, thank you. Okay, now in this case, we have given you the starting material, you have the reagent, and then all you have to do is give the product. Okay, so this should be fairly easy. So what will be the product here? What are we doing here? Okay, reducing this to CH2 and the nitro to Na2. Very good. That's easy, right? Okay, about this one here. Nitration followed by okay, what is it? Na2, very good. Okay, the first step, that is nitration. And then the second step is iron with dilute acid, and that gives you the aniline. Okay, so this is the product that we are looking for here. Okay, but this one here. Any question? Oh, Badu, sorry about that. Oh, that is a lot. I was trying to jump. Let me take this out. Okay, now we need to think about this. Okay, so this is auto para director, right? So it could come here or here. This is actually a symmetrical molecule. So in this particular instance, here we have this. Okay, so this director here, and then also let me just make some space. So nothing happens to bromine here, so this becomes, okay? Yes. I can hear you. How do you know we have to reduce it? Okay. This reagent here, this reagent here, right here, what it does is to transform an NO2, a nitro group, to an Na2. That's what it does. Okay, and the first reagent you have here gives you the nitro group. That is nitration. Okay, that's why we have nitration here. Then followed by this other reagent that gives you the Na2. So it's just a question of knowing that reagent, that is what it does. Okay. This here? Okay, this reagent, what it does is to transform a carbonate to a Ca2, and also an NO2 to an Na2. That is what that reagent does. Okay. Okay. Now let us do our C. Okay. What is the product here? What does this reagent do? Potassium permanganate. What does it do? With an alkyl group attached to benzene. What does it do? Break everything down to carboxyl group. Okay, very good. So what this does is to oxidize any alkyl group attached to benzene, oxidize all the way down to the last carbon, to the carbon that is attached to benzene. That carbon becomes a carboxyl group. So this here is going to become a carboxyl group, and this becomes a carboxyl group. All of these other carbons here will be lost as carbon dioxide. Okay, so this here will therefore be this here. So once again, you need to know what those reagents do. Because if you don't, you cannot do this. Okay, you need to know what those reagents, once you know what those reagents do, this is really very simple. Okay, now let us do the last one. This one here. What kind of reaction is this? What kind of reaction is this? Fiddle-crab alkylation, exactly. This is fiddle-crab alkylation. And now we have a methoxy group and a chlorine atom, okay, between those two, which is going to be the director here, the methoxy, because the methoxy is a greater activator than the chlorine. So I will expect the alkyl group to come to this carbon here, okay? So therefore, so the methoxy takes over the direction of this reaction, and therefore we have this here. Now, is that the only product you expect to get here? Would that be the only product? Indeed, that might even be the minor product. What do you think? Isopropyl, exactly. Because keep in mind, when you perform the fiddle-crab alkylation, you go through the formation of a carbocation intermediate. And anytime you go through the carbocation intermediate, carbocations are prone to rearrangement. Okay, so therefore, I will expect that we also get this. So I will expect to get those two products, okay? Okay, so now we finish all of the questions in your quiz. Now let us now go back and finish up our discussion on chapter 16, yes. Yes, because once you form the carbocation, there will be an hydride shift to give you, you start with a primary carbocation, which will then rearrange through hydride shift to a secondary carbocation. And that is what will then undergo that will be your electrophile to give you the isopropyl. Okay? Okay, now let us finish up our discussion on chapter. Okay, what I want to do now, I want to go very briefly go over the reaction that we call nucleophilic aromatic substitution reaction. Okay, it is not as widely used as electrophilic aromatic substitution reaction. Nevertheless, it does occur. Nucleophilic aromatic substitution reactions. Okay, as the name suggests, you will need a nucleophile here instead of the electrophile that we had in the those previous reactions. But there is a limitation to this. If you take this molecule here, for this reaction to work, you will need a very strong electron withdrawing group, like a nitro group, auto or para, to a substituent which is a good leaving group. In this case, it could be a chlorine atom or bromine atom. Okay? Now, if you do that, you have an electrophile, a nucleophile. Okay? The hydroxide could be a nucleophile here. What happens here? You could replace the leaving group, in this case the chlorine atom, with your nucleophile. Here the hydroxide is acting as a nucleophile. Keep in mind, for this to occur, the leaving group here must be either auto or para to the nitro group. For example, we could also do this here. Also get it. You can say this is a very limited reaction, but this is a very useful reaction. So what is the mechanism for this reaction? What happens if you have a molecule that in which you have the electron, a leaving group also or para to the electron withdrawing group. This pi electron here, you could actually write a resonance for this. Let me change the color of my pen. In which you could move this pi electron as a result of the fact that this nitro is pulling electron towards itself. Now form a carbocation right there. Now, at this point, the nucleophile, this time, the hydroxide simply comes in, attaches itself to this carbocation. And now what do you have? Now keep in mind, benzene always wants to retain its aromaticity. In other words, it always wants to be aromatic. So it will do anything possible to retain that aromaticity. So what happens? We have this. Okay, just as in the case of the electrophilic aromatic substitution reaction, in order for this benzene now to regain the aromaticity, what does it do? This non-bonding electron here simply comes here. It's almost like you have the your substitution reaction, in which you now have this pi electron comes here to form a pi bond between this carbon and this carbon. And knowing that carbon can only have 4 bonds, something has got to give here. Okay? So the chlorine will simply leave. And that is how you get your substitution product. Okay. Now the same thing will happen if you have the nitro group is in the para position. So the case in which it is in the para position. So again, draw your resonance. This here comes here, and this pi electron comes to this carbon. And what do we have? Okay. And at this point, the nucleophile, whatever the nucleophile is, just comes in, attacks the carbocation, okay, and now we now want to regenerate the aromaticity of the benzene structure. So what happens? we reform the carbon-carbon double bond. This comes here, and this comes here. And when that happens, we kick out the chlorine. Okay, so that's all we are going to say about the nucleophilic aromatic substitution reaction. Like I told you earlier, it is a fairly limited reaction, but it is commercially very useful. See how much time do we have? Oh, okay, we have plenty of time. Okay, now I also want to introduce you to another reaction, the formation of benzyne intermediate. If you take this, in this case also you need a good leaving group like a bromine or chlorine attached to benzene. Say we have bromine here, and we also have hydrogen here. In this case, at very high temperature and pressure, this is more of an industrial method, not a laboratory method. Say we take hydroxide, what happens here, the hydroxide comes in this case, in this time it will be acting as a base, pulling up this proton here, and in so doing leaving this pair of electrons behind to form a very strange intermediate and kicking out the bromine. This intermediate we refer to as benzyne. It is very, very reactive. Okay, very reactive. Okay, we could also, now, this benzyne, at this point, we now simply could add water to itself, the element of water to itself, so you end up with we have to regenerate the aromatic nature of the benzene structure. What happens here, imagine, just think about this here, that this pi electron comes here to grab this proton here, and the hydroxide that is going to be left off will now come here to attack this here. It's almost as if you have a concerted reaction. Everything is happening at the same time. So what is the net process here? The net process is we could very well be adding water to the benzyne, okay? And the way you get this, you start with a brominated or chlorinated benzene used, in this case, hydroxide as a base to eliminate the hydrogen bromide, and then the water will simply just add to the benzyne to form this here. You could perform the same reaction using sodium amide in ammonia. Okay, sodium amide also is capable of forming the benzyne. Okay, let me be consistent here. form the benzyne as an intermediate. And then, once you form the benzyne, now that will now react with ammonia, just as it reacted with water. Okay? Think of the benzyne coming here, the pi electron coming here to grab the proton here, and then the amino group, this here, simply comes here to attack this carbon. Now, this is also an industrial method. This here will form an aniline. This here will form a phenol. Okay, this method was actually invented in I believe in the 20s and 30s by DuPont. They made a lot of money out of this. Okay. Now, we could also react the benzyne with in a Diels-Alder reaction. For example, I could take this. Yes. Oh, go back. Okay, so I take this with amide, sodium amide in ammonia. You form your benzyne. Now you could now take the benzyne and trap the benzyne with a dye. Oh, let me just do this. Okay? And then you get this. At this point, what we are thinking here, we are going to join in a Diels-Alder reaction this here and this here, form a 6-member ring, and so we form this. Okay, you see we could actually now make fairly complex molecule. We could also take this diene, react with benzyne, to get this. Okay. Okay, we could write this in a 3-dimensional shape by simply saying, let us revisit the Occult's rule and the molecular orbital theory very briefly. Occult's rule and molecular orbital theory. Now, according to the molecular orbital theory, if you have a conjugated system flat molecule, planar is conjugated, and you have a 4n plus 2 pi electron. Let us do a schematic for that molecule. Think of the energy here. So you have p orbital here. In the case, let us take the case of benzene. We have 6p orbitals, right? Keep in mind when you draw benzene, in essence, we are saying we have all of these p orbitals here. Each one of them has an electron each. Okay? And I'm sorry, this is no, okay, one electron each. And they overlap. Okay? So now let us depict that as this here. According to the molecular orbital theory, if you have 6 p orbitals and you mix them together, you are going to form 6 molecular orbitals. Okay, so you have 6 p orbitals, you mix them together, you form 6 molecular orbitals. If you have 8 p orbitals, you mix them together, you form 8 molecular orbitals. You have 4 p orbitals, you mix them together, you are going to form 4 molecular orbitals. So now the energy level for each one of those new molecular orbitals are different. Essentially, you have one of the energy level is fairly low with only one molecular orbital, then the rest of them are paired, the same energy. Okay, in the case of benzene. Okay? So, what happens? You begin to fill up the molecular orbitals with the electrons. And each one of them will take a maximum of 2 electrons. So you have this here. The lowest one takes 2. These 2 here, which are the same energy, we say they are degenerate. In other words, degenerate simply means they have the same energy. So you give them the same amount of electrons. This in the case of benzene. See what happens here. Now, these 3 orbitals now become your what we call the bonding orbitals. These are your bonding orbitals. And the one that have no electron, we say anti-bonding orbitals. In the case of benzene, you notice here, all of the bonding orbitals are completely filled. Okay? They are completely filled. And that is why benzene is very stable. Okay? In this case, you have 4n plus 2 equals to 6, in where n must be 1. Now, if you have, say for example, we have 8 molecular orbitals, 8 atomic orbitals, for example. Let us look at the case in which we have 8 atomic orbitals. One, two, three, 4, 5, 6, 7, 8. Okay, so you have 8 atomic orbitals. How many molecular orbitals do you expect to form? 8. Very good. And then when you now form the molecular orbitals, this is what you get. You have this here. Keep in mind the first one is by itself, then the other ones are degenerate. So how many is that? That is 6, 7, 8. Okay? So you have a total of 8 electrons. Okay? So this takes 2. This takes 2. This takes 2. How many more do you have? 2 more. Okay, now since you only have 2 more, you cannot fill up these orbitals here. So this has to take 1. This has to take 1 also. Okay? So as opposed to the case of benzene, this does not have a filled molecular orbital. Okay, and that is why any molecule, cyclic molecule, the localized electron that does not obey the Ockhams rule will not be stable, will not be aromatic. And the basis for that is because they do not have a completely filled molecular orbitals. Okay? So at this point, I think we have come to the end of, I know you guys are already tired of chapter 16. We come to the end of chapter 16. I will see you on Thursday. Keep in mind when you come on Thursday, you are going to get a sheet assignment. So I will give you your sheet assignment when you come in. Okay.
All right. I was going to send you the email yesterday. I couldn't get into the group.
Just a minute.